Chapter number 11 is going to start talking about the mole. Now, before we go ahead and start talking about the mole, what I want to do is I want to give you a little background information. The thing is, when we talk about one single hydrogen atom, it has a mass of 1.67 times 10 to the negative 24th. If you think about the scales that I have in the back of the room, the best one that I have can go to 10 to the negative third. And we're talking about a hydrogen atom, and it's 10 to the negative 24th. Meanwhile, if you think of an oxygen atom, the nice thing is it's about 16 times bigger, although still only 2.66 times 10 to the negative 23rd. The thing is, the size of an atom is almost unimaginable because of the extreme smallness of it. Now, again, both of these atoms are extremely small, but the thing is, early scientists wanted a way to designate or be able to talk about the size of an atom. The unit that they came up with is going to be called the AMU. An AMU is just going to be atomic mass unit. What they would say is one hydrogen atom has a mass of 1 AMU. One oxygen atom had a mass of 16 AMUs. And what they were doing was they were weighing out a certain amount of it and then coming up with this idea of what they were going to try and classify as an AMU. When you think about how many are in a dozen, again, a dozen is just going to be a common thing that you're familiar with. It's a 12 of anything. We could talk about a dozen donuts, 12 donuts. We could talk about a dozen pencils, 12 pencils. A dozen of anything is just going to be 12. This is the standard unit, like I said, used to express 12 of any items. Chemists also needed a way to understand or express the number of atoms for a substance. The SI base unit that we talked about back in chapter number 2 is going to be the mole. It's the amount of a substance, or the base unit for the amount of a substance. The thing is, it was based on the isotope carbon-12. Chemists found the number of atoms in 12 grams of carbon-12. They knew, looking at carbon-12, that it had 6 protons and 6 neutrons. They knew that it had that number 12. So the thing is, what they wanted to do is they said, well, let's weigh out 12 grams and let's go ahead and look at it. Through many years of experimentation, it was found that 1 mole of any substance contained the same number of atoms. So if they actually weighed out 1 gram of hydrogen, they found out how many particles were in it. When they weighed out 16 grams of oxygen, they could tell how many particles were in it. When they weighed out a compound, for example, water, again, 2 hydrogens and the 1 oxygen, 18.02, again, they found out that it had a certain number of particles. The number of particles that we're talking about is 6.02 times 10 to the 23rd. That was a mole. 1 mole is equal to, and they call it Avogadro's constant, 6.02 times 10 to the 23rd. Now I want you to look there. These are the 4 units that we'll be working with. 6.02 times 10 to the 23rd atoms, 6.02 times 10 to the 23rd molecules, 6.02 times 10 to the 23rd formula units, 6.02 times 10 to the 23rd ions. Again, it could be really 6.02 times 10 to the 23rd donuts, but again, that'd be a lot of donuts, so doubt if we would ever use that one. But my point is 6.02 times 10 to the 23rd, and you fill in whatever label you need. And the thing is, as we go through the problems, again, it's going to be using those specific 4. 1 mole, like I said, is equal to, so if you actually want to see the equal part there, 1 mole is equal to 6.02 times 10 to the 23rd, and as I said, we can go ahead and fill in the label that we need. So let's go ahead and look at some calculations. Let's look at moles to particles. Let's look at particles to moles. First one, it says 0.43 moles going to atoms. And the second one is going to be 1.67 times 10 to the 25th ions. So we're going to go back to our railroad tracks. If I go ahead and look at this one again, we always start off with our given, 0.43 moles. And the thing is, it says that we want to go to atoms. So when I look at this problem, again, if we don't want moles here, and I want it gone, remember where it goes to cancel out. It's going to go opposite. We're converting to atoms. So that's going to go on top. Now on the previous slide, I'm going to go ahead and write it up here. 1 mole is equal to 6.02 times 10 to the 23rd, and then you fill in whatever unit you need. So when I look at this one, again, the mole, it got the 1. The 6.02 times 10 to the 23rd atoms is going to go there. What we get is moles canceling out. And when I take 0.43 remember we multiply on top, times 6.02 times 10 to the 23rd, I'm going to end up with an answer of 2.58 times 10 to the 23rd atoms. Let's look at the second one. This one we're going ions to moles. Again, you go ahead and start off with your given 1.67 times 10 to the 25th ions. Draw our railroad track. Ions, because we don't want them, again, they are going to be opposite of one another. This time we are converting to moles. The conversion that we have, 1 mole is 6.02 times 10 to the 23rd ions. When I take 1.67 times 10 to the 25th and I divide it by 6.02 times 10 to the 23rd, you'll end up with 27.7 moles. Okay, so again, just kind of an easy conversion between particles and moles and moles and particles. Let's look at mass to moles and moles to mass. Through their experimentation, again, it was found that the atom's average atomic mass in grams was equal to mole. Remember we said hydrogen was 1 AMU? Well, really they were pretty darn close to figuring it out back then. They just didn't have the complete technology. But what we can say now is 1 gram of hydrogen is equal to 1 mole. 16 grams of oxygen is equal to 1 mole. What we're doing is we're looking at that periodic table and we're using that average atomic mass to figure out what 1 mole of a substance is. So as I said, 1 mole of oxygen, 16 grams. 178.49 grams of hafnium, that's 1 mole. So again, use the average atomic mass that's on the periodic table. Looking at a couple of sample problems, 37 grams of iron, go to moles. 37 grams of iron, go ahead and draw my railroad tracks. Again, I don't want grams of iron, so I'm going to place it opposite. I'm going to go moles of iron here. And remember what I said, 1 mole was equal to however many grams of that substance or that element. So when I look at the periodic table, iron, it says is 55.847. 1 mole goes on top. So when I take 37 and I divide it by 55.847, I end up with 0.663 moles of iron. Again, the label moles of iron because our grams cancel out. If we look at our second one there, 1.47 moles of silver. We go ahead and convert from moles of silver to grams of silver. I go ahead and again, the mole is going to get the 1. Probably what you're going to be noticing here is the mole is always going to get the 1. I look silver up on the periodic table. 107.868. Canceling my units out, moles of silver, cancel out moles of silver. So I'm going to take that 1.47, I'm going to multiply it by 107.868, and what I end up with is 158.5659 grams of silver. Very similar, it's just you got to do a little more work than the moles to particles, because again, the moles to particles, that is always going to be that Avogadro's constant, 6.02 times 10 to the 23rd. This one you're going to have to look up on the periodic table what the mass of each element is going to end up being. Well, let's go ahead and look at the final one. We've gone from mass to moles, and we've gone from particles to moles and use those. But the thing is, we can also go from mass to particles or particles to mass. The thing is, you notice that on the previous 2 problems that we did, we had to go to moles. So that's going to be our intermediate step, or that middle step that we're going to be going through. But again, there is that relationship that can exist between mass to particles because of the mole. So if I look at this first one here, 22 grams of aluminum, and I want to go to atoms. I'm going to go ahead, it's just like the one we just got done doing, 22.0 grams of aluminum. Now the thing is, I don't want aluminum, okay? I don't want grams of aluminum. So what I have to do is I have to get rid of that grams of aluminum. And right now the only thing that we can do is we can go from grams of aluminum to moles of aluminum. Again, the mole gets the 1. We look grams of aluminum up on the periodic table and we find 27.0 grams of aluminum. If I stopped right there, I am in moles of aluminum. But again, that's not what I want. We said we wanted atoms. So I'm going to make one more railroad track. This time I'm going to put moles of aluminum there, and I'm going to put atoms of aluminum there. Again, the mole gets the 1. We go ahead and fill in Avogadro's constant, 6.02 times 10 to the 23rd. And when I go ahead and cancel out my moles of atoms, I'm going to take 22 grams. I'm going to multiply it by Avogadro's constant, 6.02 times 10 to the 23rd. I'm going to divide it by 27. And what I end up with for an answer is 4.91 times 10 to the 23rd atoms of aluminum. Finally, let's look at that last one there. It says 1.76 times 10 to the 23rd atoms of mercury. Going ahead and drawing my railroad track in. Again, we don't want the atoms, so I'm going to go ahead and put atoms of mercury down here. Again, atoms go to moles. Moles of mercury will come up on top. Again, the mole gets the 1. Atoms, 6.02 times 10 to the 23rd atoms. Atoms of mercury will end up canceling out. So you look there again, right now I'm in moles of mercury, but again, we don't want moles of mercury. We want grams of mercury. 1 mole of mercury. Looking mercury up on the periodic table. It says it's 200.59. 200.59, canceling out the moles. 1.76 times 10 to the 23rd, multiplied by 200.59, divided by 6.02 times 10 to the 23rd. And what you'll end up with is 58.644 grams of mercury.